All right, we're back with a little more discussion concerning the equilibrium constant, K. I want to make some important points concerning that. I've written down the equation again so we wouldn't forget how that works. The concentration of the products, each product raised to the power of its coefficient, that's the concentration at equilibrium divided by the concentration, the same concentrations of the reactants at equilibrium raised to the power of the coefficient. That's what we're calling K, okay? And so just want to make sure that you make a note of this. These are important points. If K is large, and these make sense just by looking at the equilibrium constant equation, right? If K is large, what does that mean? If K is large, it means this number on top of this fraction is really big, right? So it means the concentration of the products is really high. So there's more products than reactants if K is large. And so in that case, what it means is that the reaction is going to be weighted towards the products. In other words, the reaction is going to be going more in the forward direction, okay? If the reverse of that is true, if K is small, that means the number on the bottom of the fraction is really big, right? It's bigger than the number on the top. And so in that case, when K is small, then the reverse of what I said is true. It means the concentration of the reactants is higher than the concentration of the products. And so it's weighted, the reaction's weighted in the direction of the reactants. In other words, it's more in the reverse direction, okay? And so the other option is when K equals 1, then that means the reaction is balanced between the reactants and the products, and that's when you'll have this equilibrium sign, the forward and the reverse reaction going on equally there. All right, so in this case here, this is the case where K is, you can't even really see that, can you? Let me grab another marker real quick here. This top part here is the case where K is greater than 1, right? This is, the reverse happens when K is less than 1, and then as I've stated here, this is when K is equal to 1. Now, one thing to note for this course, all right, if K is greater than 1 times 10 to the 6th, we consider that to be a very large number for K, and we can assume that the reaction is just in the forward direction. Okay, it means that there's so many products compared to reactants, we can just assume that it's forward only. Conversely, if K is less than 1 times 10 to the negative 6, if it's extremely small like that, then we can assume the reaction is just happening in the reverse direction. Okay, all right, let's do a quick example. Page 489, example 16.2. And this problem reads, the following reaction has an equilibrium constant of 1.4 times 10 to the negative 25 molarity at 25 degrees Celsius. The equilibrium reaction is 2SO3, which is a gas, and then we have the equilibrium reaction symbol there. That's the reactant. The products are 2SO2, which is a gas, and plus O2, which is a gas. It says, how can this be written as a one-way reaction? And so the reason we can write this as a one-way reaction is because this K is extremely small, right? It's less than 1 times 10 to the negative 6. So actually this reaction, it would be more appropriate to say that this reaction is headed in the reverse direction, right? Like that. Now that looks really weird, right? We're not used to seeing reactions that way. And so let's rewrite this. The appropriate way then to rewrite this would be plus O2 as a gas in that direction, 2SO3. So just rewrite it so that the products become the reactants and the reactant becomes the product. Okay? So that would be the appropriate way to write that as a one-way reaction. All right, a couple more quick points and we'll be done with this section. I want to back up just a moment and consider something that we said in chapter 14. And that was in chapter 14 when we were considering the Gibbs free energy. Remember that we said that change in G, if change in G was negative for a reaction, that meant that the reaction was spontaneous, right? So remember that, change in G, if change in G is less than 0, we said the reaction was spontaneous and it would continue without any outside intervention, right? Once the activation energy happened and the reaction started, then it would continue. It was considered to be spontaneous. Well, we didn't know about the equilibrium constant at that point, so we couldn't really talk to that. But really what this means is when change in G is less than 0, it means that K is greater than 1. Okay? And in the case of that, we said when change in G was greater than 0, we said the reaction was not spontaneous and wouldn't happen. This corresponds to K being less than 1. And so it doesn't mean that the reaction won't happen, it just means that the reaction is going to happen in the reverse direction, right? Because when K is greater than 1, it happens more in the forward direction. When K is less than 1, it happens more in the reverse direction. And so the bigger the change in G is, the more that K is affected. And so like if change in G was really large, this would be, K would be very large as well, and we would consider the reaction to only go in that direction, okay? So just something to note about change in G and how it relates to K. Make sure that you remember that. The other couple of important points that I want to mention is regarding solids and liquids. This has to do with the concentration of a substance. And if you think about the concentration of a solid, it's based on the density of that solid, right? And so if I add density is, we've said when we studied density back at the beginning of the year, density is the number of grams per unit volume. So it's the number of grams of a substance over a particular area of volume, right? And so, and I put area and volume together, and maybe that's not the right way to do that. But anyway, it's the volume, it's the amount of space that it takes up, right? Well, for a solid, if you think about it, its density, if you have a solid in a reaction, its density is not going to change, because as that solid reacts and some of the solid disappears, well, so does the volume of that solid. So its density stays the same. And so the point that we want to make regarding solids is that if you have a solid, don't include it. Don't include solids when calculating K. Okay? Forgot the K there. So don't include solids when calculating K. Now, if we talk about liquids, same scenario. They're going to also, as the liquid begins to disappear, the volume will also decrease the same amount, and so its density is going to stay the same. And so don't include solids when calculating K or liquids, right? That is not the case for aqueous solutions, because remember, that's a substance dissolved in water, and its concentration can change, right? There may be less of the substance even though the volume doesn't change as much because of it being dissolved in the water. And so we will include aqueous solutions in here. But so what that means is, as far as the phases of substance, we're only going to consider gases and aqueous solutions when calculating K, okay? So let's do one more example, example 16.3. That is on page 491. And so that problem says, write the equation for the equilibrium constant of the following reaction. CaCO3, which is a solid, yields CaO, which is a solid, plus CO2, which is a gas. And this is the equilibrium reaction. And so if we're going to calculate K for this, we don't include solids and we don't include liquids whenever we do that. So neither this reactant nor this product are going to be included. And so all we have to take into account whenever we calculate K is it's just going to be the concentration of CO2 at equilibrium raised to the power of 1, because that's the coefficient in front of it. So that's it, right? That's the equation for K for that particular reaction. And then they give us one more. And this problem says, write the equation for the equilibrium constant of the following reaction. H2O in liquid form plus 2NO in gas form plus NO3, it's a negatively charged ion, aqueous, plus H plus, the H plus ion, also aqueous. And on the product side, we have 3HNO2, which is aqueous. And so in this case here, we're not going to consider the H2O, which is a liquid. And that's it. Everything else, right, is going to be included in K. So if we write down K, what we've got is going to be the products, the concentration of the product, HNO2. There's only one here, right, at equilibrium raised to the third power. All of that divided by NO, concentration of that at equilibrium raised to the second power times NO3 minus at equilibrium raised to the first power, and H plus at equilibrium again raised to the first power, right? So that would be our equilibrium constant for that particular equation. All right, we've got one more small section for this week, and so there'll be a video shortly for that.